In chapter 5 we will start applying Newton's second law, which states that the acceleration of a body is equal to the sum of all the forces acting on the body divided by the mass of the body. We will consider basic cases of equilibrium, weight and apparent weight, and finally friction and drag. This equation that Newton's second law, which states that the sum of all the forces is equal to mass times acceleration, is a vector equation, which means that if you're dealing in a Cartesian coordinate system, the sum of all the forces along the x direction must equal mass of the body times the acceleration along the x direction, and similarly sum of all the forces along the y direction must equal mass times acceleration along the y direction. Thus in the case of a Cartesian coordinate system. Now, what do we mean by equilibrium? As we discussed last week, equilibrium is when the sum of all the forces is equal to 0, which means that the acceleration of the body is equal to 0. There are two types of equilibrium: static equilibrium, in which velocity of the object is 0, that means the object is at rest, or dynamic equilibrium, in which velocity is non-zero but a constant. Before we start doing examples involving equilibrium, let's just take a look at how we would go about decomposing vectors one more time. Let's say that there is a net force F net acting on an object. Now F net will result in the object accelerating, is given by A here, and do remember that the direction of the acceleration vector is same as the direction of the net force vector. This is because of this relationship here, which where m, which is the mass of the body, is a scalar. So the direction of A and F net are the same. Now F net can be decomposed into its x and y components, and if F net makes an angle theta with respect to, let's say, the x-axis, then the expressions for F net y and F net x take these forms, where F net y is equal to F net times sine theta, is this vector right here, and F net x is equal to F net times cosine theta. Similarly, AY, which is the y component of acceleration A, is given by A sine theta, and AX is equal to A cosine theta. Let me ask you to consider this very simple example. Let's say that we have, let me switch my pen to green. Let's say that we have an object which has a weight of W, so this W vector is pointing straight down. Now if you're dealing with a Cartesian coordinate system as given by this case 1, the free body diagram is shown here, where W is straight down from the origin along the y-axis. Now the x and the y components of the weight vector are therefore given by Wx, which is equal to 0, and Wy, which is equal to minus W. Now why minus W? Because W is pointing down away from the positive positive direction of y. Now if on the other hand the coordinate system that we choose to work with, let's say because the object is sliding down a slope or being pulled up a slope for whatever reason, we're dealing with a tilted coordinate system where the x-axis makes an angle theta with respect to the horizontal plane, then once again decomposing the weight vector, remember W always points directly down, gives us wy and wx, the y and x components of W respectively, and examining these components will show us that wy is equal to minus w cosine theta. It's pointing away from the positive y, and wx is equal to minus w sine theta. As you can see, wx is a vector which is pointing away from the positive x direction. And the last case, let's say that we have a Cartesian coordinate system such that the x-axis makes once again this angle theta with respect to the horizontal plane, and in this case the w vector, when you decompose it into its x and y components, the y components remains the same, that's minus w cosine theta. However, notice that the x component of w is now a positive vector. Why? Because the x component is pointing towards the positive of the x-axis. So please take care with your plus and minus signs when you decompose vectors on the free body diagram. Let us now, let me switch, let me stay with my green pen here. Let's now consider a simple equilibrium problem. Let's say we have a box which weighs 100 newtons, alright, and it's being I guess the question is, what is the friction force needed to keep the box stationary, to keep the box from sliding down. Now, if the box were to slide down, its motion would be to the left at the slope. The slope is given at 15 degrees. Common practice is to choose your x-axis to be parallel to the direction in which the motion is taking place or would take place, and you make the positive of the axis in the direction of motion, and the y-axis, of course, by definition is perpendicular to the x-axis. Now, if the motion were to take place, if the box were to slide it down, then friction force would be towards the negative of the x-axis. So the static friction force here is pointing up the slope, i.e. in the reverse direction in which the motion, any motion would take place. Now, if you do a free body diagram of this situation, what do we have? First of all, we have our x and y axes. I've drawn it at an angle here, angle theta, which is 15 degrees. Now our w weight vector is pointing straight down. We have static friction force, which is up along the slope or towards the negative of the x-axis, and of course normal force. Now normal force is always perpendicular to the contact interface, so it's always perpendicular to the plane in which the box makes contact with the slope. So equilibrium, the box is at rest, i.e. we have equilibrium, so sum of all the forces acting on the box must equal 0, and we consider the x and the y direction separately, so the sum of all the forces acting on the box in the x direction must equal 0. Similarly, sum of all the forces acting on the box in the y direction must equal 0. So let us expand on these expressions. If we consider the sum of all the forces in the x direction acting on the box, what do we have? Well, let me scroll up a little bit. In the x direction we have wx and which is the static friction force. Now wx, looking at our free body diagram, is given by w sine theta. It is positive. Why? Because wx up here is pointing towards the positive of the axis, and fs is negative because it's pointing away from the positive of the axis, x-axis. Now w problem gave w as being 100 newtons, theta is 15 degrees, so that's sine 15 degrees, minus fs. Now fs is what we are trying to find out. That's the minimum friction force needed to keep the box from sliding, and simple rearranging of the values up there gives us fs of 25.9 newtons. So that's the minimum friction force which is required to keep the box from sliding down. Now, the question stated that a rope is attached to the box which is pulling the box up the slope with some tension T, and let's say that the applied tension T pulls the box up the slope at constant velocity, i.e. acceleration is 0. Now in this case we're dealing with friction, kinetic friction force, because the box is moving, and let's say that we know that the kinetic friction force is equal to 15 newtons. Okay, and the box still weighs 100 newtons, of course. Our slope is 15 degrees. And let's say the question is, what is the required tension to move the box at constant velocity up the slope given a friction force, a kinetic friction force of 15 newtons. Now, even though the box is moving, because it has constant velocity, acceleration 0, that means we have dynamic equilibrium, which means that the sum of all the forces along the x direction must equal 0, because acceleration along x direction, or ax, is equal to 0. Now if you do our free body diagram, you see that we have tension. In the positive x direction. We have Fk in the negative x direction. Normal force in the positive y direction, and W, which makes an angle of 15 degrees. This is 15 degrees with the y-axis. So in the x direction, the forces in the x direction, there are three forces in the x direction. There is tension, there is kinetic friction, and there is the x component of W. These are the three forces acting along the x direction, and the sum of all these forces must equal 0 because the box is in dynamic equilibrium. Tension points towards the positive of x-axis. Notice that I've switched my x-axis from the previous example. Now I'm pointing up the slope rather than down the slope. And Fk is negative, is pointing away from the positive of the axis. So is Wx, i.e. tension minus kinetic friction force minus W sine theta, which is the x component of W, must equal 0. We are given kinetic friction force, which is 15 newtons. W sine theta we can calculate, and therefore doing simple arithmetic gives us tension, a value for tension of 40.9 newtons, which means that if the tension is 40.9 newtons, then the box would be moving up the slope at constant velocity, i.e. no acceleration. And thirdly, let's say the problem asked us to find out what the acceleration of the box would be if the tension were 50 newtons. So if the tension was 50 newtons rather than 40.9 newtons, what would be the acceleration of the box? Obviously the box would accelerate up the slope because we are dealing with a greater tension than what would cause the box to move at zero acceleration. Once again, we use Newton's second law, which says that the sum of all the forces along the x direction must equal mass of the box times acceleration of the box. The expression for the sum of all the forces along the x direction is the same as what we had before: tension minus kinetic friction force minus the x component of weight. Tension is 50 newtons, the problem gives that to us. Kinetic friction is 15 newtons, that hasn't changed. And W sine theta is 25.9, that problem gives that to us as well. And all that must equal mass of the box times acceleration of the box along the x direction. Or doing simple rearranging, we get an expression for the acceleration along the x direction, which is given by 9.1 newtons divided by mass of the box. But what is the mass of the box? Well, this is when we use the definition for weight, which says that the weight is equal to mass times acceleration due to gravity. So the magnitude, mass is a scalar and weight is a vector, which always points in the direction of acceleration due to gravity. So mass is, in this case for the box, is given by 100 newtons, which is the weight of the box, divided by g, which is acceleration due to gravity, i.e. Plugging this value into the expression for acceleration gives us an acceleration value for the acceleration of 0.89 meters per second squared for the box, which means that if a tension of 50 newtons, we're pulling our box, which has a weight of 100 newtons, up a 15-degree slope where friction forces amount to 15 newtons. Then the box would accelerate up the slope with an acceleration of 0.89 meters per second squared. Let's now talk a little bit more about weight. We defined weight is equal to mass times acceleration due to gravity, and a common method to measure weight is to stand on the spring scale. Here we have Joe trying to weigh himself, so he's standing on a spring scale, and if we consider all the forces acting on Joe, well, there is his weight, W, acting downwards, and spring force from the spring scales acting on Joe. Since Joe is not moving, then and using Newton's second law, the sum of all the forces along the y direction must equal 0, since that's equal to mass times acceleration in the y direction, and AY is 0 if Joe is not moving. In the y direction, we have a spring force which is pointing up towards the positive of the axis, minus W, which is pointing down away from the positive of the axis, must equal 0, i.e. the spring force is equal to W, Joe's weight, which is, by the definition that we had earlier, is equal to Joe's mass times acceleration due to gravity. Now, if Joe has a bad habit of weighing himself in moving elevators, so let's say that he takes a spring scale, steps into an elevator, and the elevator is accelerating up with an acceleration of a in the y direction. So considering Newton's second law, what we have is the sum of all the forces along the y direction is equal to F spring minus W. Notice that the forces acting on Joe, because he's in an elevator moving up, doesn't change. We're still dealing with F spring and W as the forces acting on Joe, and that must equal Joe's mass m times acceleration that Joe has moving upwards. Since he's in the elevator moving with acceleration a, therefore Joe has an acceleration of a, and it's a positive acceleration towards the positive y, in the positive y direction. So in this case, F spring, if we rearrange the top equation here, we get F spring is equal to W plus MAY, but W is equal to mg, therefore F spring, which is a measure of Joe's weight, is equal to Joe's mass, m, which doesn't change from the case where he was stationary, into g plus ay. Now notice that in the stationary case, Joe's weight was equal to, well, F spring was equal to Joe's weight, which is equal to mg, but in this case F spring is equal to m into g plus ay, which is greater than mg or w, and this is what we call apparent weight. So what Joe would measure in an accelerating elevator is his apparent weight, and if the elevator is accelerating up, his apparent weight would of course be greater than his actual weight. Now if we consider the elevator accelerating downwards, i.e. ay is a negative value, then going through a similar analysis, we see that F spring minus W is equal to m times minus ay, because now acceleration is downwards, and in this case we end up with F spring, or the apparent weight, is given by mass, Joe's mass, times g minus ay, i.e. apparent weight is now smaller than the actual, or Joe's stationary weight, his actual weight. Finally, let's consider friction forces. Let's consider kinetic friction. Kinetic friction, shown by Fk, is a vector which has a magnitude equal to mu kn, where mu k is the coefficient of kinetic friction. And you can take a look at the table 5.1 in chapter 5 for typical values of coefficient of kinetic friction for, let's say, wood on wood, steel on steel, rubber on concrete, etc. And do remember that the direction of kinetic friction is always opposite of motion, the direction in which the motion is taking place. And in this as far as the magnitude of kinetic friction goes, as I said, it's equal to coefficient of kinetic friction times normal force n. So if you have an object on a surface, if you know what the normal force is, and if the object is, let's say, moving to the right, of course kinetic friction force would be to the left. The magnitude of kinetic friction force is given by a coefficient that you look up in a table times the normal force. That's the magnitude of the kinetic friction, and its direction is opposite that of motion. So to consider a simple example here, let's say we have a wooden box being pulled on a wooden surface. So if you look at table 5.1, you see that the kinetic friction for wood on wood is equal to 0.2. So that's the kinetic friction coefficient that we'll be using. And let's say that the tension by which we're pulling the box to the right is 50 newtons. The box has a weight of 100 newtons. Notice the box is moving to the right. And the other forces involved, of course, are normal force, because the box is in contact with the surface, and kinetic friction. If you do a free body diagram of this scenario, we have our XY coordinate system. X is pointing in the positive to the right. That's the direction in which motion is taking place, and we have tension to the right, friction force to the left, W pointing straight down, and normal force pointing straight up. So in this case, if we say that the box is moving but the acceleration in the x direction is 0, i.e. the box is in dynamic equilibrium, so let us now try and calculate what actually, let me take that back. The box is accelerating to the right, so let's figure out what this acceleration is that the box has moving to the right. First of all, even though the box is accelerating to the right in the x direction, we know that the box is not accelerating in the y direction. So the box along the y direction is in equilibrium. That means the sum of all the forces in the y direction, which, looking at our free body diagram, is equal to normal force minus weight, is equal to MAY, which is, since AY is 0, the whole thing is equal to 0. This means that our normal force is equal to our weight, which is equal to 100 newtons, as the problem has given us. Now, along the x direction, the forces are T, tension, and Fk, which is negative towards left, and that equals MAX. Once again, this is from Uncle Newton's equation. So problem has given tension to us as being 100 newtons, but we don't know what Fk is. However, we can calculate Fk by using this expression, which is mu k times n, coefficient of kinetic friction, times normal force. We just calculated the normal force as being 100 newtons up here, which we can plug into this equation down there. Mu k we look up in our table as being given by 0.2. Therefore, the magnitude of friction force is equal to 20 newtons. So plugging 20 newtons back into this equation here gives us 50 newtons, which is our tension, minus 20 newtons, which is our friction force, equal to mass times acceleration in the x direction. And AX is what we are trying to find out. Therefore, AX is equal to 30 newtons divided by mass of the box. And once again, mass of the box is equal to weight of the box divided by acceleration due to gravity, i.e. doing simple math, we end up with AX is equal to 2.94 meters per second squared. Therefore, looking at our drawing here, if we have a box which weighs 100 newtons being pulled to the right with a tension of 50 newtons, where the coefficient of kinetic friction is equal to 0.2, then the box would accelerate to the right with, I forgot the value, I believe it was 2.9 something meters per second squared. Yes, this was actually 2.94 meters per second squared. Now, let's now consider static friction. Static friction force exists between two objects which are stationary with respect to each other, in contact with stationary with respect to each other. Its direction is opposite to the direction in which motion would take place if there were no static friction, and its magnitude is less than or equal to mu s n. Once again, n here is our normal force, and mu s is the coefficient of static friction. Which you can take a look at table 5.1 for some typical values. So if you have a box which weighs W, which is being pushed to the right with a force F push, but the box is not moving, then it's at rest. Then if we were to plot static friction force versus F push, we end up with a straight line which has a slope of 1. Our slope is equal to 1, i.e. Static friction force is equal to F push till a maximum value, Fs max. So throughout this region here, our object is at rest. There's a linear relationship between static friction force and the F push, the applied force to our object. Notice that if F push is equal to 0, well, static friction force is equal to 0. The harder you push an object, the greater the static friction force is, till you reach this limit, Fs max, beyond which the box would slip and start moving, in which case we move into kinetic friction mode, which we discussed a few minutes earlier. Now, doing a free body diagram for our box, once again we choose our Cartesian coordinate system, x, y. W is pointing directly downwards, normal force up. I forgot to show the normal force here in the drawing. We have F push to the right and static friction force to the left. Now, I should also mention that the maximum value for static friction force is equal to mu s times n. So now, if the problem had asked us to find what is the maximum force, F push, that will still keep the box. Actually, let me back up. Let's say the question is find what is the maximum force needed to start getting the box to move. Well, what we can do is, looking at our free body diagram, applying Newton's second law in the x and the y directions. Let's take a look at the y direction. And the sum of all the force in the y direction is equal to mass times acceleration in the y direction. Ay is 0. The box isn't moving up and down, so the whole thing is equal to 0. in the y direction, what do we have? We have normal force minus W, that must equal 0, i.e. normal force equals W in this simple case. Now, similarly, in the x direction, the box isn't moving, so the whole sum of all the forces in the x direction must also equal to 0. What do we have in the x direction? We have F push and static friction force minus Fs. And the maximum F push is, when we have maximum F push, we have maximum static friction force. Therefore, F push is equal to Fs max. That's a maximum push force that the box can withstand just before it starts moving, just before it slips. And Fs max is given by mu Sn, as is shown up here. Since we know we are dealing with wood on wood, so it's a wooden box, let's say, on a wooden surface, using the coefficient for wood on wood for static friction, which is 0.5. Once again, this is from the table in chapter 5. We can then calculate what the maximum F push the box can withstand just before it starts slipping. So plug in the values. We have 0.5 times normal force, which is equal to Rw, and W, if you recall, was equal to 100 newtons. Therefore, the box can withstand a F push of 50 newtons just before it starts slipping. So once again, plotting the friction force versus F push while the box is at rest. The static, we are dealing with the static friction force. So this is the static friction area region, where the static friction force increases linearly till a maximum value Fs max, as we start applying greater and greater F push, and then after it hits Fs max, just after it hits it, the box slips and starts moving, in which case we are now in the kinetic friction mode, where the kinetic friction force is given by, let me get rid of that, where the kinetic friction force is now constant, equal to Fk, and the box is now accelerating as a result of the F push being applied, a greater and greater F push being applied. So in general, coefficient of kinetic friction is less than that for static friction. That's why for those of you who've tried to move something heavy across the floor, if you push and it doesn't move, you typically jerk it. You kind of give it a push, give it a kind of jerk it a little bit, get it moving. That reduces the coefficient of friction between the object and the floor, and then you can push it more easily, because the you shift from static friction region to kinetic friction region, where friction forces are smaller. And one last friction force type to discuss is a rolling friction. I'm just going to mention it for the sake of completeness. We're actually not going to be using rolling friction in our problems, but I'll mention it for sake of completeness. Rolling friction force, Fr, has a constant value which is given by mu r n. Once again, mu r is the coefficient of rolling friction, which and n is our normal force, and its direction is opposite that of motion. So if we consider the tire of a car rolling to the right, tire is made out of rubber, road is concrete. The coefficient of rolling friction between rubber and concrete is 0.02, as is given in our table 5.1 in this chapter. So if you know the normal force on the tire, then you can go ahead and calculate the rolling friction force for this scenario. Finally, let's talk about drag or air resistance. Drag is a friction type force. Its direction, once again, is opposite to that of motion, and its magnitude is a function of the velocity. Its magnitude increases as the velocity of the object increases. Coming up with an exact relationship for drag is not trivial. It depends on a number of parameters, but if you consider a simplified model in which the object has a diameter of a few millimeters to a few meters, and the velocity of the object doesn't exceed 1000 meters per second, and we consider the object moving in dense atmosphere or near Earth, then we can obtain a relationship for the drag force, where the magnitude of the drag force is approximately given by 1/4 of the area, the cross-section of the object, times velocity squared, the square of the velocity of the object. Now A is the object cross-section. That's the so if we have, let's say, a sphere falling towards ground, then the cross-section that affects drag is the shaded area here, which is equal to pi r squared, where r is the radius of the sphere. If we have a cylinder falling head first down, then the cylinder's radius is r. Then once again the cross-section in this scenario is also equal to pi r squared. If the cylinder were falling on its side, where the cylinder has a length L, and once again the radius is r, then the cross-section affecting drag is equal to 2rl. And if you have a cube falling, then the cross-section, of course, is equal to a times b, where a and b are the length of the sides that are in the plane perpendicular to the direction in which the cube is falling. So as an example, if you consider a sphere of mass m, so we're dealing with a sphere of mass m and radius r free falling, then here's our sphere, and the two forces acting on it, of course, are its weight and drag. Weight is given by mg, and the magnitude of drag is 1/4 of pi r squared a, where pi r squared is, of course, the cross-section of the sphere. So we now ask ourselves what would be the maximum velocity which this falling sphere would reach. That maximum velocity, by the way, is called the terminal velocity, and terminal velocity is reached when there is no more acceleration involved, i.e. At v terminal A is equal to 0. So there's our object is no longer accelerating. So the sum of the forces acting on the body must equal 0. The two forces acting on the body are weight and drag, i.e. at terminal velocity W must equal D. That's the magnitude of W must equal D. W is mg, or the magnitude of W is mg, and magnitude of drag is 1/4 of A, the cross section, times square of the velocity, but in this case the terminal velocity. Therefore, an expression for terminal velocity can be obtained in this form, which is square root of 4mg over A. So for any object, terminal velocity can be calculated if you know the cross section of the area, cross section of the object and its mass. So as an example, let's see what would be the terminal velocity for a skydiver. Let's say he or she has a mass of 75 kilograms, and as a quick estimate of his or her cross section, let's say, is 1.8 meters in height and 40 centimeters width. So that gives us an area cross section of 0.72 meters squared, which, plugging this value and this value into this equation, gives us a terminal velocity of about 64 meters per second, or 140 miles per hour. That's pretty fast. Don't try this at home. A plot of velocity versus time. If there is no drag, of course, this red line shown here, which is a straight line with a slope of -g, and with drag, of course, we reach a plateau, where this plateau is the terminal velocity. Notice that the way I've drawn it, since the norm is to have y pointing up, my velocity, since it's down, is falling, is in the negative region. Well, what I like to do next time we meet is work through some examples applying Newton's second law, using the expressions for friction and drag, and making use of equilibrium arguments.